Hi everyone. In this video we will make use of what we saw last week regarding conditional probabilities and incorporate a new notion which is called partitioning. A partition is a procedure that is frequently used when the realization of an event is influenced by an underlying event. For instance, car insurance companies evaluate risk based on the age and the sex of the driver, the type of car he or she is driving, and the amount of travel that is anticipated. By definition, let's suppose E1, E2, A3, and so forth represent mutually exclusive and exhaustive events of omega, the sample space. Then, the union of E1 with E2, with E3, and so forth is called a partition of omega. In other words, a partition is made up of events that fulfill all of omega while having no mutual intersections. A consequence is that if E1, E2, E3, and so forth is a partition of omega, then any event A can be written as a combination of the intersections of A with E1 or E2 or E3 or En, and combined as a union with the other intersections. So just to rephrase that, we can actually visualize, notice how event A here can be decomposed, which is actually what partitioning means. Event A can be decomposed into its intersection with E1, with its intersection with E2, its intersection with E3, and so forth until we run out of the partitioned events. None of these events are intersecting, so nothing is double counted. This also means that the probability of A occurring, and here you can visualize on the Venn diagram, is obtained by adding all of the little areas where A intersects with the partitioning of omega. So here we have the probability of A, which consists of its intersection with A and E1, and then we can add the probability of A's intersection with E2, and then add the probability of A's intersection with E3, and so forth. So essentially, P of A is the sum of the probabilities that A has with the partitioning, or the individual partitions of omega. As we mentioned earlier, the occurrence of event A may be dependent on the occurrence of the partitioned events E1, E2, E3. So in this case, conditional probabilities may be actually useful. Now recall that by definition, the probability of A conditional to EK is equal to the probability of its intersection of A with EK divided by P of EK. Here K obviously could stand for 1, for 2, for 3, so these are all the sub-partitions that we have for the sample space. This means that the probability of A's intersection with EK can be rewritten as the product of the probability of A conditional to EK times P of EK. Now in the previous slide, that means that rather than having the sums of these individual intersections, we could express P of A as the sum of the probabilities of A conditional to each of the EKs times the probability of those EKs. For instance, studies conducted by the Santé Publique du Québec reveal that 85% of citizens over 60 years old state they are willing to be vaccinated against COVID-19. This proportion drops to 70% for those who are in the 41 to 60 age group, and to 50% for those whose ages are 21 to 40. Note that 28% of citizens that are over the age of 60, 32% of the population consists of people between 41 and 60, and 40% are aged between 21 and 40. If a Quebec citizen of age 21 or more is selected at random from the Quebec population, what is the probability that this person will be willing to be vaccinated? Now, if we translate the information we have just gathered, 28% of the citizens are in the 61 and above age group, 32 are in the 41 to 60, and 40% are between 21 and 40. So essentially, we could define the events A1 as being the person selected is 61 years of age or above, A2 is between 41 and 60, and A3 is between 21 and 40. We're picking a person at random, so we are unaware of what the outcome will be, but we do have probabilities for each of these events. In fact, P of A1 is 28%, P of A2 is 32%, and P of A3 is 40%, according to the demographics that we have. As we keep going in translating the information, we said that Santé Publique says 85% of citizens over 60 years old are willing to be vaccinated. And this proportion drops to 70 for the 41 to 60 age group and to 50 for the 21 to 40 age group. So notice how all of these are conditional probabilities. They are based on the fact we know the age of the person. So the individual is willing to be vaccinated. If we use V to represent that event, well, according to the data, P of V knowing A1, so knowing it's a person that is older than 60, we get 85%. P of V knowing A2 is 70, and P of V knowing A3 is 50. So all these probabilities are conditional to age. So it seems that the age is a factor that influences a citizen's opinion with regards to vaccination. Hence, the population can be partitioned by age, which is what I've chosen to do here. Notice how omega has the 3 different age groups, none of which intersect, and they are exhaustive in the sense that we are only focusing on individuals 21 and older in the survey. Consequentially, we can decompose the event V into 3 intersections. Its intersection with A1, or A2, or A3. We don't have information about the intersections, but we do have information about the conditional. So we're going to try to find a way to make that link. So here's an image of how P of V can be decomposed into the probabilities of the 3 partitioned elements. All right, so now, as we said earlier, intersections can be converted into conditionals. So for every intersection, P of V intersection with A1, we've rewritten it as P of V knowing A1 times P of A1, and so forth for the other subsections. At that point, things clear up a little bit, because we know that if someone is in the age group called A1, so 61 and over, there's an 85% chance this person will be willing to be vaccinated. But this population consists of only 28% of the group. And so we repeat the process for other age groups. And in the end, the probability that a randomly selected person will want to be vaccinated is 66.2%. In the same context that was described previously, suppose a respondent says he or she is not willing to be vaccinated. Find the probability that he or she is in the 21 to 40 age group. First, let's translate what is represented in the question above. It says that we are aware that the person refuses to be vaccinated. So that's V bar. So we are assuming, we know that event V bar is respected or satisfied. And the probability we're looking for under these circumstances is that the person is in age group called A3. So P of A3 knowing V bar. Starting with the definition, the probability of A3 conditional to V bar is P of A3 and V bar divided by P of V bar. We can visualize the numerator as being the area in A3 but excluding the intersection. So here we're using properties from operations on events. So from P of A3 we will remove the probability of A3 knowing intersection with V. P of V bar is the complement of, or is equal to 1 minus P of V, since V bar is the complement of V itself. If we write A3's intersection with V, or V's intersection with A3, it makes no difference. That's the same region. And then we can convert this intersection back into a conditional, P of V knowing A3 times P of A3. All of these elements are now known. P of V, which we solved previously by partitioning, P of A3 and P of V knowing A3 were given in the information. So now it's a bunch of number plugging. In the end, you would get 59.2.